Hi, I'm Grant Hogue from Boston Children's Hospital, and this is the Scoliosis Dialogues, the one and only official podcast of the Scoliosis Research Society. A few updates for listeners or those watching this on video. IMAST early registration ends on March 11th. The meeting is in San Diego this year and looks to be an excellent program. The SRS abstract submission deadline is February 1st at 11:59 Eastern Standard Time. So make sure to have all of your data back from the statisticians and have your abstracts in time. And so for our podcast today, we have the winners of the inaugural Douglas Burton Award for 2023's Best Adult Spine Deformity Manuscript. This award is named after Dr. Burton, who was actually featured on this podcast just last year and has served as deputy editor of Spine Deformity, the official journal of the SRS. Their project that has won the award is entitled Proximal Junctional Failure After Surgical Instrumentation in Adult Spinal Deformity, a Biomechanical Assessment of Proximal Instrumentation Stiffness. And so we're fortunate to discuss this paper with lead author Maeva Lopez and senior author Carl-Eric Aubin. Thank you so much both for coming today.
Thank you first of all, we are very grateful to have received the first Doug Burton Award in recognition to our research work, and I'd like to thank the SRS for this.
Excellent. And so I'd say really maybe the first question for both of you, and Maeva, maybe you can answer first for us, is that, many, maybe most of readers of spine deformity are practicing physicians, but undoubtedly we lean heavily on brilliant engineers and people who have more of a biomechanical background than even, perhaps we do. And so how did each of you become interested in spine deformity, and how do you leverage your knowledge and skills as an engineer to get us to do different things on the clinical side?
Interesting question. So first, thanks. I'm happy to be here. For this, I think that mainly it's a discussion between engineers and clinicians. So we need to make research and more understand the biomechanics of the spine to help spinal surgery, but mainly we need to focus our research in the ways that it can help. So clinicians.
So anything to add to that?
Yeah, Joe, I would just like to add that over the past 30 years, my main objectives in my research lab was to address, from an engineering point of view, practical problems faced by the orthopedic surgeons for the treatment of complex spine deformity. And as Maeva mentioned, it's a close dialogue to really understand the problems and see from a interdisciplinary point of view how we can bring our knowledge together to help improve the technologies to improve the surgeries.
Yeah. And how did you initially become interested in spine deformity?
I can begin, because for me it's kind of more easy. I was interested in biomechanics since my engineering diploma. I was more interested in spine biomechanics because I had the opportunity to begin the PhD with Carl-Eric. And this is where, so I found the subject really interesting. And to have those close dialogue with surgeons wants me to continue in this thematic and begin my PhD. But then it's more like Carl-Eric at the beginning.
Yeah.
Yes. On my side, I was always interested by the pathologies, the medical field, but from a technological point of view. So really the type of research I'm doing is really applied research, close to the clinicians, try to understand the problems and bring solutions. But working together, we can improve things. So this is which has motivated me.
Oh, that's fantastic. And so in my world, like junctional failure, junctional kyphosis, whether it's proximal or distal, is something that just keeps us awake at night, right? Whether you're taking care of children or adults. And so for you, what was the impetus for this project in looking at the biomechanics of proximal junctional failure?
Okay, first of all, proximal junctional kyphosis or proximal junctional failure is a complex challenge because it is still a problem with following long instrumentation. And even if there are many identified risk factors, little is known about the importance of biomechanical factors because it's difficult to measure them clinically and or control them in practice. So on your X-ray, you cannot see a force or stress or strain on the spine or on the construct. So this is where we can bring engineering tools, the same that are used to analyze planes or other structures for the human body. So we are just using those tools combined with medical imaging and clinical practice to have a first order assessment of the forces and stresses on the construct. And using also other engineering tools, we can then simulate and test various options, various configurations, do what if we do this, what if we do this instead of this, and then figure out the one that will put less stress on the construct and minimize the risks of further complications.
That's excellent. And so in your paper, you talk about all of the different options. And so you used different rod thicknesses, right? So different rod stiffness, as well as different anchor points. So laminar hooks, pedicle screws, and sublaminar bands. And so can you speak a little bit about building this model in kind of the digital realm on a computer and also your methodology for validation?
I can take this one maybe. For the we previously have developed multi-body model to enable the simulation of spinal fusion. So we can, with that, have the assessment of biomechanical effort. So as Carl-Eric said, the forces and moment in the spine, the geometry, so the curvature of the spine at the end of the simulated operation. And so this allows us to have the impact of various strategies, such as so which implant do you use in this article, or which maneuvers do you use, which correction you choose. So this is a base with a multi-body model, which have the physical laws to represent the spine and the instrumentation. Then we can also have it adapted to each specific geometry of a patient. Using lateral and coronal radiographs, we will have the 3D reconstruction to have the specific geometry of the patient. And then we can also adjust the flexibility if we have the flexibility film tests. With that, so we can first, what we try to do is to ensure the representativeness of the patient and its surgery. So basically, we are taking the post-op radiograph of the patient and we compare every main angle, such as thoracic kyphosis, lumbar lordosis, and everything, to what we have simulated. If we have this representativeness, we can then try to, one at a time, change a parameter. And this is where the numerical model shine. So we can test different implants or different roads and everything. So this is the baseline. Then for the validation, so in a previous article, we have tried to follow the ISMEV and V4T guideline to validate for its context of use. So for all the entire of my PhD, it was for proximal junctional kyphosis and failure. So basically, we tried first to see if with biomechanical forces, we can see a difference between a cohort of patients who have developed PGF and asymptomatic ones. We find that mainly the sagittal moment at the UIV, between UIV and UIV plus 1 on the anterior spine, was discriminating between those two cohorts. So we can continue with simulations and try different type of implants and roads and see what may differ in terms of biomechanical force.
Thank you.
May I just add one also another thing which is original here is to assess not only the forces and moments at the upper instrumented segment, but also above. and to analyze how the forces are balanced when doing various with various rod curvature or osteotomies or things like that. So we can also play with the model to figure out ways to best balance the loads. And also in this paper, we also analyze the gradient, so the change of force between the instrumented and non-instrumented spine. So we found we compare various options, and there are ones that are, let's say, that have a very important gradient of moment of forces that will more likely be more risky to develop PJK as opposed to a more gradual change. So these are additional things that we introduce in this paper.
One of the things you discuss in the paper is that as you decrease stiffness to have a more gradual or even kind of the soft landing type atmosphere, you increase the possibility of rod breakage. Mm-hmm. And so what have you learned is kind of the sweet spot, and can that be dialed in at a patient specific level?
Yeah, I can take this one, or Maeva. The thing is, it's very we need to be careful not to generalize for every case, because every case is different. It's highly case specific, and given the biomechanical nature of the risks, we need to use a customized approach and a patient specific approach to balance the forces and minimize the transition of the gradient of forces between the instrumented and non-instrumented. So we have seen in the paper that a less stiff proximal construct is helpful, but depending of the presenting deformity, if there's a lot of correction proximally, then they will need some forces to do it. So we need to so there could be different strategies depending of the presenting deformities.
And this might be beyond the context of what you're presenting here, but would you say that these findings are most pertinent kind of in the immediate post-operative period before a fusion takes place, or is the chosen construct still a significant PGF variable after a fusion is formed?
I can take this one. This paper is mostly in this biomechanical model for just after surgery, before the fusion. Because first, this is where the spine is the most imbalanced, and this is where you will have the most forces inside your spine and also your instruments. Then when you will have fusion to occur, you will probably have change of load that may be really interesting to check for more longer complication. Then also for PGF, it normally appears within 6 months, so before fusion. So it was more appropriate to check before the fusion. So.
Yeah. Of course, there are also other events that could lead to PGF, which are like accidents or things like that. So these are additional things. But with the model, we can test alternate options. So for instance, if we like to see what happened after fusion, then we can reuse the model, but change the conditions in the model to address this other interesting question.
Oh, excellent. Thank you so much. Sorry to make you speculate. And so as we get closer to the end of the podcast, so what can we expect from your group in the future? Perhaps even upcoming at IMAST or the SRS meeting.
So this project is continuing in my research chair. We have several students, grad students, and research assistants continuing to work on this problem because it's not yet solved. The idea is still to continue further to develop clinical application tools to better plan instrumentation and reduce the risks of PJK and PJF. We intend to combine AI, artificial intelligence, which are based on data and patterns observed in large data sets, and also our deterministic models, which are based on fundamental laws of physics and mechanics. And with these tools, we intend to do a multi-dimensional optimization. So not only taking into account the functional realignment of the spinal correction by playing with the route contour and the material and the type of implants, but also to minimize the stresses and the forces in the construct to reduce the risk of PJK, as well as to include other elements such as value-based approach that considers patient outcomes, economics, safety, OR time, and other elements such as neurological risks, cost, and so on.
Yeah. Well, that's wonderful. And so, Dr. Lopez, Dr. Aubin, thank you both so much for being here. Thank you for this contribution to the literature, but even more than that, thank you for advocating for patient-specific, curated, and bespoke care. I hope you
Thank
both.
You very much.
Yeah, I hope you both have a great day, and I hope to see both of you in San Diego at IMAST.
Yeah, and we look forward to continue the collaboration with all the surgeons to find solutions for the patients.
Excellent. Thank you so much. Have a great day.
Thank you. Bye.
The Scoliosis Research Society is a nonprofit professional organization made up of physicians and allied health personnel. Their primary focus is on providing continuing medical education for healthcare professionals and on funding and supporting research in spinal deformities. Please visit srs.org for further information.